Quantum reality, what the math actually says in under 3 minutes. Episode 6, the Quantum Zeno Effect, how quantum computers use measurement to freeze out errors. Measure a qubit fast enough and you can freeze it in place. Not slow it down, but actually prevent it from changing. This is the Quantum Zeno Effect. Quantum evolution has a strange property. When a state first starts to evolve, it doesn't immediately leak into other states. There's a startup phase where the system is rotating internally, but it hasn't actually begun changing in a way measurement can detect. The math says this explicitly. The Hamiltonian, the operator governing evolution in the Schrödinger equation, makes the probability of transition grow quadratically with time. This is all to say that this t squared is the whole game. It means at very short times, essentially nothing probabilistic has happened yet. The rate of change starts at 0 and has to ramp up. So if you measure repeatedly, say n times in a total of time t, each individual measurement catches the system before it's barely started evolving. Make n big enough and this approaches 1, perfect survival. This is totally different from classical physics. If you have classical radioactive decay, it's exponential from the instant it starts, and checking it more often doesn't matter. You still get the same exponential curve. But quantum mechanics has this forbidden zone, at short times where probability change hasn't kicked in yet. Measurement exploits that, and you keep resetting the clock back to that zone. That's how quantum error correction works. You rapidly measure certain properties to create protected subspaces. The quadratic startup law becomes your engineering tool. Tune your measurement rate to freeze the error while letting your computation proceed. Next, quantum teleportation. How to make a particle vanish in one lab and appear in another without ever existing in between.